first experience in Investigation 3 on gravitational forces is about universal gravitation. What does this mean in everyday language? Basically, we learn about the force of gravity, and without giving away too much, find that the rules of gravity are universal. They apply on Earth the same way they apply anywhere else in the universe. Cool, right? So that's what's meant by the term universal gravitation. And in this experience, our key objectives are to represent gravitation mathematically, to be able to predict gravitational forces, and explain the idea of gravitational forces in space. In this lab exploration, you'll investigate the factors that affect a pendulum and use your data to determine the acceleration of gravity on Earth. Before we get started, we launch the inquiry with a demo that models something with an enormous amount of gravity: our sun. Okay, I've got a good one for you here. If hot gases on Earth spread out, why does the sun have a spherical shape? This question stump you? Boil some water on the stove, or let the air out of a tire, and once those gas particles are free, you're never getting them back. Yet the sun is a huge ball of gas, right? So why is all the gas collected in the shape of a sphere on the sun, but that doesn't happen here? Let's take a look at this reaction between baking soda and vinegar in an Erlenmeyer flask. I'll pour just a small amount of vinegar into the flask first, and that's around 40 milliliters. And then I'm going to drop a few grams of this baking soda powder into the vinegar, and we'll see what happens. Okay, so watch as I pour this in. And what do we notice happening? Make sure all of it gets dumped in there. What do you see? It's bubbling, it's fizzing. Let me make sure I get all of it in there. Yeah, lots of bubbles in there, huh? So, it's bubbling, it's fizzing, but, well, actually nothing spectacular is happening, right? What? No explosion, no special colors. Sorry if that was a little bit anticlimactic. Let's do it again, but this time we won't let our eyes deceive us, as I'm going to attach a balloon to the outside of the flask, and the baking soda is going to drop from inside the balloon. So, using the same ingredients, what differences do we notice this time? Okay, so I've got the balloon, and I gotta be real careful right here because when I expand this over, sometimes it tears. All right, I think I got it. So inside the balloon right now is the same amount of that sodium bicarbonate, which is just baking soda. And I'm going to pour it inside and, what do we notice now? The balloon expands. Okay, so it's still bubbling and fizzing just like before. But what do we notice that's different this time? So what do you think actually happened during this reaction? The evidence is clear that gas was produced from the chemical reaction between the baking soda and the vinegar, as this is what inflated the balloon. We didn't see the gas the first time, as the particles were invisible to us. So the main difference between the first and the second reaction is that the gas was allowed to escape the flask and spread out the first time, but the balloon held the gas in place in the second reaction. So, maybe you can try to answer why the sun has a spherical shape now. Well, it should be no surprise that this can be explained by gravitational forces. And on the sun, those forces pull all of the gaseous mass towards the sun's center. And that results in a spherical shape. So let's go one question further then. If the gas inside the balloon represents the sun's gaseous body, what could the balloon represent? You got this one, right? Tell me you got this. I know you've got this answer. Yes, you're absolutely right. The balloon itself would represent the sun's gravity. Well, okay. Now that we've got your brain warmed up, let's get started with the lab. So, as mentioned previously, you get to explore gravity using a pendulum in this lab. And that's the title of the lab: Investigate Gravity Using Pendulums. The lab's essential question is, how does gravity affect the motion of objects on Earth? You don't need many materials for this lab to collect your data. Just a string and a bob to hang and swing, and some measuring tools like a protractor and timer. What can the characteristics of a pendulum teach us about the gravity here on our planet? Let's take a look at the lab overview video.
A pendulum is a simple device that converts gravitational energy into kinetic energy back and forth. As such, pendulums can be used to investigate Earth's gravity. Ideally, a pendulum consists of a weight suspended from a frictionless pivot point by a massless rod. In the lab, pendulums are typically built using a metallic bob of known mass, a thin string, and a support. The time it takes for a pendulum to swing back and forth is known as the pendulum's period, represented by capital T. For small release angles theta, a pendulum's period is inversely proportional to the square root of the acceleration due to gravity, represented by lowercase g. This is expressed in the following equation, where period, represented by capital T, equals 2 times pi times the square root of the ratio between L, the length of the pendulum, and g, the gravitational acceleration on Earth. How would you determine the value of the gravitational acceleration g using the equation for the period of a pendulum? What measurements would you need to perform? In this laboratory, you will use pendulums to investigate gravitational forces and to determine the value of the gravitational acceleration on Earth, represented by lowercase g, and the universal gravitational constant, represented by capital G.
Okay, so you saw the video that you will be creating a pendulum by tying some string to a mass and swinging it from a stand, taking some measurements, then doing some mathematical calculations. So yeah, the lab is pretty simplistic from that perspective. The video mentioned a term, period, written as capital T. This is the time it takes the pendulum to swing back and forth in one complete cycle. So now, we've got to think about the characteristics of the pendulum that we can change to find any relationships with this period. Ask yourself, what can I change about the string and the mass to investigate any effect on the time it takes the pendulum to swing back and forth? In fact, there are 3 things you can change about the pendulum that you'll explore in this lab, and you probably thought of them. You can change the length of the string of the pendulum by swinging with strings of different length. You can change the amount of mass hanging from the string. And you can also change the angle from which you release the pendulum. So to be clear, this means you will have 3 independent variables to explore in this lab, as you'll be changing 3 components of the pendulum. So, let's go over the setup of the materials so you can get swinging soon. First, get about 75 centimeters of string and thread one end of the string through the large mass, tying a knot around it. Now you've got your pendulum. Simple, ain't it? Now take one of those big clamps and secure it to your table. In this slot, place a metal rod and tighten it so you've got a post. At the top of this rod, attach a ring clamp, and again, make sure it's tightly secured. From here, you can hang your pendulum by using a clip or clothespin to clamp onto the string from the ring, like this. Test that your pendulum can swing freely. You want to avoid anything that might get in the way and hit it. Once you're free of obstructions, you're just about ready to get started. You just need to be clear on some procedural steps as you modify your pendulum. First, to measure the period, get a timer and press start upon release of the pendulum. We recommend you time for 30 seconds, and you're going to count the number of complete oscillations, or back and forth swings, in that time period. Every time it returns back to its release spot is one oscillation. So for example, you'd count like this: 1, 2, 3, and so on. You will repeat this step for 3 trials each time you make a change to the pendulum. When changing the release angle, place the protractor like so, and pull the pendulum along its swing arc to the desired angle away from its resting or equilibrium position. Here's 5 degrees. Here's 10 degrees. And here's 15 degrees. So the timing and counting process will remain the same every time. But as you're going to be modifying the length, the mass, the release angle, hold this general rule of thumb. Only one thing should be changing at a time. Or, stated a different way, keep everything else constant. So when you are changing the length of the pendulum from 20 to 30 to 40 to 50 centimeters in length, keep the mass and the release angle the same for each change in length. By the way, measure from the top of the string to the center of the mass to be accurate. And use a release angle of 5 degrees. Now when you're changing the release angle from 5 to 10 to 15 degrees, make sure to use the same length and the same mass for each change. Use 50 centimeters for the length when testing the release angle. And when changing the mass, use the same length and the same release angle. Again, 50 centimeters for the length, 5 degrees for the release angle. As long as you're keeping everything aside from your independent variable constant, your data collection should be free of error. Now, you'll notice in your data tables that there are columns for period and g, which is the symbol for acceleration due to gravity on Earth. These values will come from calculations that you can save for after your data collection. So, all you need to do while using the pendulum is count oscillations in each 30-second time frame. Once you've all your data, you can calculate period by dividing 30 seconds by the number of calculations you counted. You can round your value to the hundredths place, which is 2 places after the decimal. So get to investigating. Be detailed in your consistency and sharpen your measurement. Then see what your data teaches you about the motion of a pendulum and subsequently the gravity here on Earth. Enjoy.